so forth. I just want to emphasize how very important it is, as soon as you get done with the do it, to have somebody come up here and get started on the homework. What we want is efficiency. This class is very good with talking, I think probably because it's first period and kids are still kind of quiet, and like Mary almost looks like she's sleeping right now. So what happens is this. Classes that talk a lot and the teacher has to wait for the class to get settled down, those classes, every time the teacher has to wait 30 seconds, if they do it 10 times in a period, that's 5 minutes. And if they do 5 minutes a day during a week, that's 25 minutes long. That's more than half a period. So that works out to like 90 periods a year. I'm sorry, 20 periods a year that they're not learning when that little bit of talking is going on. It doesn't really matter how you waste time. It doesn't matter if you waste time doodling. It doesn't matter if you waste time talking. And it doesn't matter if we waste time in not getting the homework checked as quickly as possible. So when you do the do it, if you get to the end, please don't be shy. Come on up and get this because, you know, as a teacher, I have to take care of attendance. I got to take care of making sure, you know, things are in order and things are ready to go. And some of the things I can take care of when you're not in the room, but some of the things have to be taken care of when you are in the room. And as such, if you guys check all of that stuff off, it saves us an extra minute or two a day, and maybe even a little bit longer than that, maybe 5 minutes in a day. And then that's more time for you to learn. So efficiency is a super, super, super deal. All right, so now we're morphing into a new type of question. The last couple of days we talked about function terminology, and one of the things we did was we talked about the fact that you could graph a function. Now, everything that we've graphed so far has had a constant rate of change. It was a line. And when I graphed it, it looked like that. Constant rate of change. Always, God bless, never varies, never deviates, always the same rate of change. Well, now we're going to do something slightly different. I'm going to scroll this up, and then I need you guys to read to me a little bit. By the way, what we're going to do today is all about what we call piecewise linear functions. And this is a case where the rates of change can vary. And vary means to be able to change, all right? And we want to be able to determine the rate of change at any particular point in time and maybe some real world situations. So we got this really big graph going on here. And this problem is about wrapping presents, okay? Is there anything in this problem that suggests that we're dealing with super big numbers? No. Okay, good. Sometimes it does. If you remember yesterday, we did a problem near the end of class that involves some super big numbers. So I can go and use pretty much a typical scale. And then on this side, I can do a typical scale too. This is all in the first quadrants because I cannot get negative presents, despite what you may believe at Christmas. And you cannot have negative time. I wish we could have negative time. I wish we could go back in time and correct things. Now, Hunter, read me the first sentence, please.
Todd finds a job wrapping presents during the Christmas season.
Good. Second sentence.
At first, when he is just learning, Todd wraps one present per minute.
For how long?
For 5 minutes.
Is that what it says? You're reading it like you don't know.
No, it doesn't say it yet. It says Todd wraps one present
Per minute. At the 5th minute. So that means from up until the 5th minute. Okay, so he does one per minute. So at time 0, how many presents has he wrapped? 0. 1 minute later, how many presents has he wrapped? 1. Another minute later, how many has he wrapped? Another 1, so a total of 2. Another minute later, 3. Another minute later, 4. Now it says at the 5th minute. Have I hit the 5th minute yet? No. So at the 5th minute, something else is going to happen. But for now, I can graph that part of the function. Okay? So this is called a piecewise linear function because it's almost going to look like the graph is made up of pieces. Now, does it make sense in real life that when you first learn how to do something, you're a little slower at it than you are a little while later? Right? Does that make sense? Okay. So now what happens starting the 5th minute? White Sox, what do we got?
John starts to go faster and wraps 2 presents per minute.
For how long?
He does this for 3 minutes.
For 3 minutes, he does 2 presents per minute. Now, 2 per minute mean I have to go up 2 presents over 1, up 2 presents over 1, up 2 presents over 1. He does it for 3 minutes, so that's it. Can you see that the slope of the red segment is different than the slope of the blue segment? Does that make sense? Now, what is the slope of the blue segment? 2 per minute. And if we do that in a more, that would be what we call a rate, and slope is a rate of change. We would say this slope is up 2 over 1. This slope would have been what? Up 1 over 1. Does that make sense?
Yes.
Okay. Now, what starts happening with the graph? Who wants to read the next part? Emma, go ahead.
Now at the 8th minute, Todd has no presents to wrap for 2 minutes.
Okay, so he has no presents to wrap for 2 minutes. So here we go here, and this rate of change would be 0. Okay? All right, and who wants to read the next section, which I think is the last section? Go on, somebody else, volunteer, raise a hand, let's go. Fire. Okay, 3 presents per minute for 3 minutes. Todd's really boogieing here. All the presents are pretty tiny. 3 presents in 1 minute, 3 presents in a minute, 3 presents in a minute. There's my graph. And for what it's worth, this slope would be 3 over 1. Now, you do not need to write the slopes on this. I did that for the purposes of instruction. Okay? That is a piecewise linear graph. Okay? So what I would like to do at this particular point in time, at the bottom it says, what is the average rate of change over the given intervals? Now, average, when you take your test, right? In here, let's say you have 4 tests, and your grades are 100, 100, 100, and 90. How do you figure out your average?
Add them all together and then divide them by how many.
That's right.
there
Add them all together, divide by how many are. So what we're going to do here is we're going to add up all the minutes and divide by how many there are. So, let's see, I'll go to that, and I'll go to this, and I'll go to this. So, I'm going to go from here up to there. Pretend that's a straight line, okay? And then I'm going to figure out, this started at 0, 0, right? Oh, hold on, I gotta get to solid line here. This started at 0, 0, and it ends at this point here, which is 10, 11, 12, 13, right? 8, 9, 10, 11, 12, 13. Yup, this is 13, comma, and the height is 18, 19, 20. Does that make sense? This is the point 13, comma 20? You have 12? 9, 10, 11, 12. I have 13.
12.
Did you do, when you did this, did you stop with 4 dots or 5?
4.
4, yeah, but it says at the 5th minute it changes. So you had to do the 4th one to the 5th one. Okay, so that's why you're off by 1. Now, how much we say that we want to find the average rate of change. Now, the rate of change formula is slope. And slope is the change in y over the change in x, okay? Another way to look at the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Which of those formulas did Mr. Frank use last year? Did he use the first one or the second one? First one? All right, I like the first one too. Okay, this little triangle means change. It's delta y, it means the change in y over the change in x. Now, if you see the second one, don't get scared, okay? All this means, everybody look here so you can make sense, because this is really simple. It means the y from the second point minus the y from the first point over the x from the second point minus the x from the first point. That's all it means. So, if I do the y's, I have to do 20 minus 0 over 13 minus 0. So the average rate of change is 20 over 13. And rate of change is slope. Slope often looks like a fraction. So though it's kind of a little bit weird, leave it that way. Fractions are normal in the context of slope and rate of change. Okay? Now, we are going to do lessons for 3 days about piecewise linear functions. So it's not like you have to suddenly understand how to do this right this very minute. You should feel a little awkward. Some of this you should look at and say, okay, I get that little bit, I get this little bit, I kind of get that. But when I put it all together, I'm really not seeing the whole thing here. and we have a couple of days to get through this, okay? Any questions? All right, let's keep working on this just a little bit more. Next page. All right, so now we got some video of a guy that goes up and down the stairs. All right, so, oh, this isn't gonna work. It's not gonna work because the laptops that the district gave us do not play YouTube anymore.
So can't you look up on
What's that?
that? Can't you look it up on that?
But that's really a pain in the butt. It's really, really annoying. Here's what happens with the section. The guy turns around and he starts up high, and then he walks, and then he walks, and then he walks on a level piece of ground, and then he walks down steep stairs. Okay? So what you can see is it pretty obvious that the rate of change if you walk on something like this is not going to be the same as a rate of change like this, right? And that if he walks on level ground, then there is no rate of change. So you're going to get three lines that kind of look like they did in the last graph. Now the cool thing is, I have another graph right after this that they already did for you. So, come on. Come on, there we go. Behave. Da-da-da-da-da-da. Here we go. Ready? Let's go up to 125% so we can see a little bit better. Here's an elevation versus time graph for a person's motion. Now, this is very, very, very important. You always got to peek and see what this is. Oh, there we go. This is elevation. What does elevation mean? Guys, talk to me. What's elevation? Height. Very good. And this is time. So notice, this is not a graph of necessarily how fast a person is walking. It's a graph of how high they are above the ground at any particular point in time. So here we have, notice this is a 5, this is a 10, and this is a 15. So there's a scale there, and this is a 2, 4, 6, 8, and 10. So let's talk about this for just a second. From time 0 until time, call that 3, this person is going up at this rate. Agree? Now, if he goes from 0 to 10, how far did he go up? 10, right? If you go from a height of 0, or an elevation of 0, to an elevation of 10, what has been your increase in height? 10. Over, and how long did it take him to go up 10? 3 seconds. So we would say, okay, that rate of change is 10 over 3. Okay? I know you might want to convert these things to a decimal, but be comfortable with fractions. Learn too big. Now, over the next second, from 3 to 4, what happens to the elevation? Stays the same. He doesn't get any higher. Does he get lower? No, he stays exactly the same. So this would be the height change is 0 over 1. Okay? Now, from time 4 up to here, I don't really know what that ends up at. Whatever, I don't care. I'll skip that part. What's the rate of change from here to here? 0 again. Can you tell that anytime you have a perfectly horizontal piece, the rate of change will be 0? Right, this is the third time we've hit that. All of a sudden, what happens to the next rate of change, which goes, and rate of change is just like slope, which goes from here all the way down to here. And let's just say that comes out to 7 seconds. And let's say this starts at 6 seconds. Oh, I don't want to put a height of 6, but it goes from 6 to 7 seconds. What do you notice about that height? He's going what? Down. What do you think I need to include if something is going down?
Negative.
Negative. So the first thing is that this particular rate of change is going to be negative. Now, I'm going from a height of 15 down to a height of, and I'm just going to say that this height is 1. So if I go from a height of 15, an elevation of 15, to an elevation of 1, how far did I go down? 14. And I did it in, from 7 to 8 seconds, 1. And it's almost like they fell down the stairs. Okay? And then to go from 7 to 8, I stay the same. So again, that's 0. And then here, I go down 1 in 2 seconds. So it's down 1 over 2. And there is my piecewise linear function. Remember what we said today was all about. It's a piecewise. So the rates of change throughout the problem. Here, it's going up 10 over 3. Here, it's going up 0 over 1. Here, I kind of ignored because it was tough to find it, what numbers we matched up to. Over here, we go 0. Here, we go down 14 over 1. Here, we go 0. And there we go down 1 over 2. Does anybody come up with an idea what this person might have been doing? Climbing a mountain. Okay, well, that mountain's about 15 feet high. It's a tiny mountain. Go ahead. Okay, no, I like it. We're getting creative here. He's climbing a hill, not a mountain, trips and falls, splat. Then what happens? He does what? He walks a little bit, or he... Well, the bottom line is he has to go up a little bit more, so maybe he, like, mountain climbs kind of and reaches up and grabs the one little ledge thing sticking out in the other one, and he pulls himself up real quick, and then he gets to the top of the mountain. And then at this point of the mountain, he starts going...
You said mountain.
Yes, because you did. Now, all of a sudden, when he's in the middle of his dance, what happens? He trips and falls. Splat! Slamming his head on the ground 1 foot above the ground, and then he's like, oh.
There is a cliff.
What?
There is a cliff.
Could have been a cliff. Could have been a cliff. We could do this in hundreds of feet.
Yeah.
And then we get like lots of blood here. Okay. Now, and then he slowly gets his wits about him. And he walks slowly at a gentle angle back down to the ground. Okay? So, what we have here is piecewise linear functions, little bits at a time. This is our beginning of trying to understand this. We're going to do more about it tomorrow, which is what, Monday? You get Face Friday, right? Yep. So, Wednesday, that's right. And we're going to do another lesson on this Wednesday and another lesson on this
We have homework.
Thursday. You have what?
Homework.
Always, every single day. You find the word homework from that point forward. Okay? Are we good, guys? Excellent day. You can start your homework now if you wish.
So I guess I have to leave, right?
You have to, oh,